In section 3.2, we're going to discuss polynomial functions and their graphs. Let's let n be a non-negative integer and let a sub n minus 1, all the way down to a sub 0 be real numbers with the property that a sub n is not equal to 0. We define the function a sub n x to the n plus a sub n minus 1 x to the n minus 1 up to plus 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 down to a sub 0 to be a polynomial function of degree n. These subscripts you see with these coefficients just kind of tell you which power of x that they go with. For instance, if we look at a sub n x to the n, a sub n is the coefficient. The power term would be x to the n. A sub n refers to the coefficient of the n power term. Similarly, if you look at, let's say, the coefficient here, a2 would represent the coefficient of the x squared term all the way down to a sub 0, which would represent the constant term that goes with no power of x. The reason why we want a sub n to be non-zero is because we want to be able to explicitly state out what the leading term is. And in this case, if a sub n is not 0, then this is going to be the highest power of x in our expression, and that's called the leading term. The coefficient of that leading term, which would be a sub n, is referred to as the leading coefficient. We would also say that this is a polynomial of degree n because n is the highest power of x that appears in our sum. To get some examples of polynomial functions, let's look at lowercase f and g. Here, f would be a polynomial of degree 5 because 5 is the highest power of x. The leading coefficient, which would be a5, has the coefficient value of 3. If we were to multiply g of x, so g of x is not in standard form, it's actually in factored form, but if you were to multiply this all the way out, you would ultimately see that g of x would be a polynomial of degree 6, whose leading coefficient would be negative 3. If we look at these other two functions over here, capital F and capital G, these ones are not functions that are polynomials. The reason why f is not a function, capital F, is because of the square root of x term. If you have fractional powers of x, so it's very important that we come back here, that n has to be a non-negative integer, so that these are all positive integers, or possibly 0. If you have things like fractional powers of x or radicals, or even divisions of x terms, then those things cease to be polynomials, and they would belong to some other class of functions. So here, the reason why capital F is not a polynomial is because of the square root of x term. Notice that you can have coefficients that involve square roots. The square root of 2, for instance, is a real number. That won't prevent a function from being a polynomial, but having a square root of the variable will. G of x is kind of a non-polynomial for the same reason. Excuse me. We know that we can rewrite the 1/2 power is equivalent to the square root of x. And so for the same reason as f, g is not a polynomial either. One of the next things we want to do is discuss the graphs of polynomial functions. Polynomial functions have graphs that are referred to as smooth and continuous. These two definitions have very precise meanings in something you'll discover if you take a calculus class. The notion of continuous is simply that you can kind of draw the graph without any jumps or breaks or gaps in it. You can draw it with, without having to lift your pen or pencil off of the paper. The notion of a graph being smooth, in essence, means that it has no sharp corners or jagged edges. It's nice and rounded. You have no sharp turns in it. Okay. So for example, if we look at a graph of a polynomial function, this is exactly what we see. It has nice rounded shape to it. There's no sharp corners like you would see with like an absolute value kind of thing. And there's no jumps or gaps in the graph. So these are examples of graphs of polynomials that are both smooth and continuous. If we take a look at these two graphs over here, neither one of these could have been the graph of a polynomial. The reason why the first graph could not be a polynomial is because this function actually has a gap or a break in it. If you try to draw this function, by the time you get to this one particular value of x, you would have to lift your pencil off of the paper to pick up and continue drawing it slightly below it. And because of that gap, that means that this graph would be that of a function that is discontinuous at that value of x. If we look at the next graph, the one here to the most left, this one is actually continuous. You can draw this graph without having to lift your pencil off the paper. So while it is continuous, the issue with this graph is that it is not smooth. And the reason why this graph is not smooth is because here and here you have sharp corners. So that means that that graph also cannot be the graph of a polynomial, because we know that polynomials must be both smooth and continuous for all values of x. One of the next things that we want to discuss is what's referred to as the end behavior of a function, and we're going to investigate the end behavior of a polynomial. The behavior of the graph of a function very far to the left or very far to the right is called its end behavior. Essentially what you're looking at is what happens to the function values, the outputs, when the absolute value of x gets large. In other words, when you have either really, really large negative inputs or perhaps really, really, really large negative outputs. Inputs. It's nice that when we deal with polynomials that they can be entirely categorized for their end behavior based upon what's called the leading coefficient test. So in a polynomial, even though it contains multiple terms, if we take a look at f of x here, f of x would be a polynomial of degree n. It turns out that the leading coefficient and the leading term entirely determines the end behavior. Okay? These lower order terms also contribute to the graph of the function, but what they kind of impact more or less is the number of turning points you have, as well as where the zeros of the function would be located at. But the end behavior is entirely determined by the leading term, and this is what's called the leading coefficient test. We have two cases, first of all, whether the leading exponent is odd or even. And let's start with the easier case first. If we have a leading power of x that is even, okay, then the end behavior is consistent on both sides. Furthermore, if n is even, we need to consider the subcase about the sign of the leading coefficient. If a sub n is greater than 0, then the polynomial will both rise towards positive infinity as x approaches negative infinity. So if we go far to the left, the graph is going to rise up towards positive infinity. And if we go to the right, if x approaches positive infinity, the graph will also approach positive infinity. Usually we have a notation to describe this. I would explain this graph as follows. We would say that as x, let me make some more room here, that as x approaches negative infinity, we would say that f of x approaches positive infinity. Also, as x approaches positive infinity, in other words, as we go over here far to the right, we see that the graph keeps going up and up and up. So we would say that f of x approaches positive infinity. In the textbook, sometimes you'll see them use the shortcut notation up and up. This just means that the graph approaches positive infinity to the left, and it approaches positive infinity to the right. On the other hand, if the leading coefficient is less than 0, in other words, if it's negative when the leading exponent is even, then the graph is going to fall to the left, and it's also going to fall to the right. So for that one, we would say that as x approaches negative infinity, so if we look at really far out here to the left, if we keep going out and out to the left, we see the function is going to go down and down and down, and f of x will approach negative infinity. Similarly, as x approaches positive infinity, so if we go over here far to the right, the graph will continue to go down and down and down, and f of x will also approach negative infinity. If you wanted a shorthand for this, it goes down to the left, and it goes down to the right. If it helps, I've seen a lot of students that kind of like to use x squared as a representative example for this. In an earlier lecture, when we were discussing the graphs of like families of graphs, we mentioned the fact that, at least in terms of n behavior, x to the n for n even behaves very similar to the graph of x squared. So if you think about what x squared looks like, it goes up to the left and up to the right, like our parabola. And so this is kind of a representative example for what you would see if you had a positive leading coefficient and an even exponent. An example of n even with a negative leading coefficient, we'll just think of like negative x squared. That would be a parabola to be inverted downwards like this, and obviously it goes down to the left and down to the right. The same thing would be indicative of the n behavior for any polynomial with an even powered leading term and a leading coefficient that is less than 0. For n odd, if n is odd, again, we have to consider two cases. When n is odd, if the leading coefficient is positive, kind of reminiscent of what you would see with like x cubed, which looks like this, those graphs will fall to the left and rise to the right. So they go down to the left, up to the right. But if the leading power is odd and the leading coefficient is negative, again, think of something like a negative x cubed, whose graph would have been reflected, it would look like this. Those ones actually end up going up to the left and down to the right. So this is very convenient for us. We can determine the end behavior of a polynomial simply based upon the leading term. From there, again, there's kind of 4 cases you have to break it down into. First thing you'd want to look for is what type of leading exponent do we have? Is that leading exponent odd or is it even? And then from that, the next thing you'd want to determine is, what is the sign of the leading coefficient? Is the leading coefficient positive or is the leading coefficient negative? Again, here's a handy little chart where you can see it's broken apart into the 2 cases. First of all, there's the power of n. It's either odd or even. And then the leading coefficient, whether it's greater than 0 being positive or less than 0 meaning negative. Again, I typically find for most students, the even case is the easier one to memorize because the behavior is consistent within each sub-example. It goes either up and up in both left and right direction, or it goes down and down in both left and right direction. The odd case is the one you got to be on the lookout for because it'll do one type of behavior on one side, namely here, if n is odd and greater than 0, it'll approach negative infinity as x approaches negative infinity, but yet it'll approach positive infinity as x approaches positive infinity. So it's kind of the opposite on either side when n is odd. Let's use the leading coefficient test to determine the behavior of the graph of the polynomial f of x equals x to the 4th minus 4x squared. So we look at it, we see that the leading term is the x to the 4th. Our a sub 4, the leading coefficient, is 1, which is positive, and the degree of this polynomial is 4, which is even. Whenever we have an even positive exponent, leading exponent, and a coefficient, leading coefficient that's greater than 0, we know that's going to go up to the left and up to the right. So that would be our end behavior. Certainly on the exam, you can write it like this. With an eye towards the future, it is kind of good to get it used to the writing kind of like this notation. What's happening on the left-hand behavior? Well, what's happening is as x approaches negative infinity, if we look out very, very far to the left on the x-axis, what we would see is that the function values would be approaching positive infinity. And in the other direction, as we look at what's happening on the right-hand side, as x approaches positive infinity, we see that f of x is also approaching positive infinity. So this is the end behavior for this function. Let's take a look at example 2. We again want to use the leading coefficient test to determine the end behavior of the graph of f of x. What makes this one a little bit interesting is the fact that we actually don't have it written in standard form. It's actually provided to us in factored form. But we know at the end of the day, if we're only concerned with the end behavior, all we need is the leading coefficient. And you can find that. You can find the leading term from the function f in factored form by doing the following thing. If you have any part out in front, write that like this. So we have negative 4x cubed. And then just think about from each little factor, what part of it is going to contribute to the leading term. Anytime you have a parenthesis, the highest power inside of x inside each parenthesis will ultimately multiply out and lead to our leading term. So if I look inside the first parenthesis, the leading term within that little subportion of it is going to be the x. And likewise, the leading term within this little subparenthesis is going to be x. And when we kind of multiply all those leading terms together, it'll give us a leading term overall for the full polynomial f of x. So this is going to be negative 4x cubed times x squared times x, which is going to be equal to negative 4x to the sixth. So we have the case where n is even. We also have it where a sub n is negative 4, which is less than 0. So that's going to be the situation where it's going to go down and down. As x approaches negative infinity, when we go to the left, the graph is going to fall. So it would be the case that f of x would also approach negative infinity. And as x approaches positive infinity, meaning as we go to the right here, f of x will also approach positive infinity. The next thing we're going to look at is the zeros of a polynomial function. If f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of the function. They're also sometimes referred to as the roots, the solutions of the polynomial equation f of x equals to 0, and graphically they correspond to the x-intercepts of the graph of the polynomial function. Let's take a look at some examples. In example 3, we want to find all zeros of f of x equals x cubed plus 3x squared minus x minus 3. In general, finding the zeros and solutions of a polynomial function can be quite difficult. We will talk about some more advanced methods later in this section of how to do so. But for right now, kind of our key main techniques are the ability to factor and then set each factor equal to 0. And in example 3, that's what we can do. We're going to set this equal to 0. This would give us x cubed plus 3x squared minus x minus 3 equals to 0. This is an expression that contains 4 terms, and we recall from algebra that a lot of times if you want to factor something with 3 terms, it's a good idea to try to do factor by grouping. So let's group the first 2 terms together. Let's group the last two terms together, and now let's pull out the GCF within each parenthesis. In the first grouping, we can factor out an x squared. That'll leave us with an x plus 1. In the second grouping, there's a common factor of negative, so factor out the negative 1. That'll leave us with an x plus 3 equals to 0. And I made a mistake over here. If you factor out the x squared, that's a coefficient of 3, not 1. Now that we're here, we see that both expressions have a common factor of x plus 3. So we can factor that term out. And what we're going to be left with is x squared minus 1 equals to 0. So we were able to factor it according to factor by grouping. But notice that this factor here can be broken down even more. That's the difference of squares. That piece factors as x plus 1 times x minus 1. And now that everything is completely factored, just go ahead and set each piece equal to 0. And I'm running out of room, so I'll put this one down here. Solve each resulting linear equation. Subtract 3 from both sides. If we get 1, 0, it's x equals to negative 3. Subtract 1 from both sides here, we get x equals to negative 1. And add 1 to both sides, and we get x equals to positive 1. Let's take a look at example 4. Again, we want to find all zeros of this function. So we're going to go ahead and set f of x equal to 0. That is negative x to the fourth plus 4x cubed minus 4x squared equals to 0. Here, we again have a GCF we can factor out. Let's factor out not again, but we do have a GCF here. Let's factor out the negative x squared from all of our terms. That will leave us with a positive x squared minus 4x plus 4, like this. So we were able to factor it. We factored it with a GCF. Now notice that the resulting quadratic we get, that also factors more. This factors as x minus 2 times x minus 2, which is equal to 0. And if you wanted to, you could write it in exponential notation because we have a repeated factor here. We get negative x squared times x minus 2 squared equals to 0. Now we want to set each factor equal to 0 independently, like this. We could divide both sides by negative 1. We get x squared equals to 0. Take the square root of both sides, but plus or minus the square root of 0 just gives us a value 0. Here, again, take the square root of both sides. Square root of 0 is 0. And then add 2 to both sides. We get x equals to 2. Coincidentally, one of the things that you might notice is that for each of these, when we set each of these factors equal to 0, we ended up taking the square root, but in either case, it ended up being plus square root of 0 and minus square root of 0, both gave us the value 0. When that happens, you don't necessarily have to include the exponents here. You can just set the part under the exponent equal to 0 directly. So I could set x equal to 0, x minus 2 equal to 0, and we would still get the same two values, x equals to 0 and x equals to positive 2. These exponents, though, so for these factors, these exponents are important, and they're related to something which is called the multiplicities of our zeros. Okay. When we got the solution x equals to 0, this came out of a factor, namely this factor here, which was the negative x squared part, which was raised to the second power. We would say that x equals to 0 is a 0 of the function with a multiplicity of 2. And the reason why it has multiplicity 2 is because it kind of appears as a factor twice. If you to rewrite it like negative x and x, set those pieces equal to 0, it's producing essentially two factors, both of whom give the solution x equals to 0. Okay. When we have our polynomials factored, if the same factor, let's call it x minus r, if this occurs k times, but not anymore, not k plus 1 times, then we say that r is a 0 with multiplicity k. So coming back to this previous example once again, both 0 and x equals to 2, which were zeros of these polynomials, both would have multiplicity 2 because the factor x appeared to the second power in the complete factorization, and the factor x minus 2 appeared to the second power in our factorization. Another reason why this is kind of important is if you remember the fundamental theorem of algebra, and we talked about this, it's that any polynomial of degree n has exactly n zeros or n solutions in the set of complex numbers. So if we look at our starting polynomial, this was a polynomial of degree 4. If we come down here and if somebody says, oh, the zeros of this polynomial are of 0 and 2, how do we reconcile that with the fact that we should have 4 solutions? Well, we kind of do. It just happens that the 0 happens to have a multiplicity of 2. So the 0 is occurring as a solution kind of twice, if you will, and then the same thing for the other solution, x equals to 2. It also appears with a multiplicity of 2, and so there, if you kind of write it out like this, you can explicitly see the 4 solutions that would be guaranteed by the fundamental theorem of algebra. One of the implications, and things that's going to be very important as the multiplicity of an intercept pertains to the graph is the multiplicity will determine what happens when a graph of a function of a polynomial crosses the x-axis. For example, if x equals to r is a multiplicity of an even value, so if you have an even multiplicity root, then what happens is that whenever the graph crosses, or excuse me, whenever the graph gets that intercept, what it's going to do is it's going to touch and turn around. It's not going to cross through like this. Or perhaps it could look something like this. So when you have an even multiplicity root at r, that's what happens. It touches and it turns around. If you have a root that has an odd multiplicity, then at that value, the function will cross through the x-axis. Okay? Either like this, or perhaps if I have another odd root here, it'll cross through like this. So the multiplicity does tell us some important information about the graph of the function, namely what happens when the graph reaches the x-axis. We know it has a 0 there, so it's going to be on the x-axis. When the multiplicity is even, the graph touches and turns around, and when the multiplicity of a 0 is odd, then the graph will pass through the x-axis. Let's take a look at example 5. We're asked to find all of the zeros of the function f of x, give the multiplicity of each 0, and then state whether the graph crosses the x-axis or touches the x-axis and turns around at each 0. So let's go ahead and do that. First thing we want to do is find the zeros. And if you hadn't already done this, the first step would be to put this thing in factored form. Luckily for us, that step is already done. And now what we're going to do is we're going to take each of the linear factors. You don't have to include the exponents here. Just whatever is being raised to a power, whatever makes those things 0, 0 to any power will be 0. So we set the stuff underneath equal to 0, like this. And these are going to give us our zeros. For the first one, you just subtract 1 from both sides. We get x equals to negative 1. For the second one, you would add 3 and divide by 2. We get x equals to 3/2. And then for the last one, you would add 4 to both sides, and we would get x equals to 4. So our intercepts are the following values. I'm going to put them in order from least to greatest, which they already are. We have x equals to negative 1. We have x equals to 3/2. And we have x equals to 4. The next thing they want to know is what is the multiplicity of each of these zeros. For the intercept x equals to negative 1, that came from this factor right here. There's no exponent explicitly stated, so we know that it's going to be to the first power. The 0, x equals to 3/2, came from this factor, which is raised to the second power, so it has a multiplicity of 2. And then the 0 or intercept x equals to 4 came from this last factor, which had a power of 5. So it has a multiplicity of 5. So we have an odd one, an even, and an odd for these. The last thing we can talk about is now the behavior at the 0. Remember, if it's odd, that means it's going to cross through the x-axis. So this graph would cross the x-axis at x equals to negative 1. With an even multiplicity, it's going to touch and turn, meaning it's not going to cross through the x-axis. It's going to come, it'll touch that point, and then it'll turn back around. And then x equals to 4, again, this is an odd multiplicity, so it will cross through the x-axis. In the link for this lecture video, I will actually graph this function for you. I'll include a link below. And what I would like you to do is look at the graph and actually verify visually what we found here. Make sure that when you look at the graph, that you see the graph crossing the x-axis at negative 1, that you see it touching and turning at x equals to 3/2, and that once again we see the graph crossing through at x equals 2 to 4. One of the next things that we're going to discuss is something called turning points of a polynomial function. The graph of f of x equals x to the fifth minus 6x cubed plus 8x plus 1 is shown below. We know that the end behavior of a polynomial is determined by the leading term, but the kind of lower order terms help to contribute to things like zeros and as well as things called turning points. This graph has 4 smooth turning points. So we have a turning point here. Here's 1 here, 2. There's another one here, 3. And then we have 1 down here, which is at 4. A turning point you can think of as it's any point where the graph changes from either increasing to decreasing. As we see here, it goes from going up to going down, or vice versa, it goes from decreasing to increasing, going down to going up. Again, to be a polynomial, it has to be both smooth and continuous. So those turning points are nice and rounded. They're not sharp corners at all. In general, to actually find the turning points is a pretty involved process and requires the use of calculus, but we can at least state the following information. If a polynomial is of degree n, then the graph of f will have at most n minus 1 turning points. Okay, so for example, if we have a polynomial of degree 5, which we do up above, then it will have at most 5 minus 1, which should be equal to 4 turning points. Okay, and for this particular example, that's exactly what we see. We had a polynomial of degree 5, and we ended up with 1, 2, 3, 4 turning points altogether. Okay, be very careful. You don't always get exactly n minus 1. They say that in general you get at most a number of turning points that is 1 less than the degree of the polynomial. A simple example of this is if you look at the graph of x to the 6th, according to this, we would get at most 6 minus 1, which would be 5 possible turning points. However, in practice, in actuality, x to the 6th only has 1 turning point, and that's at 0. So be very careful. It doesn't tell you exactly how many you get, but it does give us an upper bound for the most amount of turning points that would be possible. The next thing we're going to get into is a strategy for graphing polynomials. The first step we want to do is use the leading coefficient test to determine the graph's end behavior. The next thing we want to do is find our x-intercepts by setting the function equal to 0. For us, the main technique for solving this is going to be to factor it, and we want to put it in a factored form that will allow us and help us to see the multiplicity of each intercept. We can then categorize each intercept based upon its multiplicity in terms of what it means for the graph. For any x-intercept with an even multiplicity, we know that the graph is going to touch and turn around at the x-axis. For any 0 of odd multiplicity, we know that the graph of the function is going to cross through the x-intercept at that point. We can also find the y-intercept, which is another important point on the graph, by evaluating f of 0. We may want to, on occasion, investigate to see whether the function is even or odd, to see if we have any kind of symmetry that might reduce the amount of graphical work needed. Remember, even functions would exhibit y-axis symmetry, and odd functions would exhibit origin symmetry. And then when we graph it, just to kind of fact check ourselves, make sure that we have at most n minus 1 turning points. Let's go ahead and take a look at example 6 here. Okay. In example 6, we're asked to graph f of x equals x to the 4th minus 2x squared plus 1. So first things first, let's determine the end behavior. So if we look at the leading term here, it's going to be x to the 4th. The value for n is 4, which is even. And the leading coefficient is understood to be 1, which is greater than 0. So for the end behavior, I'm just going to write it with the shorthand. We know that this graph is going to approach positive infinity as x approaches negative infinity, and it's going to approach positive infinity as x approaches positive infinity. So we know the end behavior. The next thing we want to do is let's see if we can find the x-intercepts. So we're going to set f of x equal to 0 and solve this. That is, when is x to the fourth minus 2x squared plus 1 equal to 0? This is a fourth degree polynomial that also so happens to be reducible to a quadratic. Some of you may be able to factor it like this. If you're struggling, you can always use a u substitution. Let u equal to x squared. And then this would become u squared minus 2u plus 1. And it's a basic quadratic in the variable u. I'm just going to go ahead and factor it as it is. This will factor as x squared minus 1 times x squared minus 1. So it factors like this. And then notice that each one of these is a difference of squares, so they factor even more. We get x minus 1 times x plus 1 for the first factor. And the second one also factors as x minus 1 times x plus 1. We can write this more compactly as x minus 1 quantity squared times x plus 1 squared equals to 0. To find the zeros of this function, the intercepts, you don't have to set the entire part, but just the part under the exponent equal to 0. X minus 1 equals to 0. X plus 1 equals to 0. This will give us the solution x equals to 1. This will give us the solution x equals to negative 1. So we get two x-intercepts. They are x equals to negative 1, x equals to positive 1. Notice we can discuss the multiplicity. Both of these zeros came from factors that had an exponent of 2. So both of them have even multiplicity. And that means that we know the behavior of the graph at those zeros, or of those intercepts. They're going to touch and turn. So this graph will not cross through the x-axis at either of those two zeros. We can now go ahead and find the y-intercept. To find the y-intercept, it's an evaluation. We do f of 0. This is 0 to the fourth minus 2 times 0 plus 1, which should be equal to 1. So we have the order pair 0, 1 on the graph. Coming back over here, we could have even stated this here, but our x-intercepts were the order pair 0, negative 1, 0, positive 1. And if we wanted to investigate a little bit more, this graph is actually going to be even. Okay. If you check for symmetry, I'm not going to show the work. I'll leave that up to you. We did this in the last section. But f of negative x is equal to f of positive x. So f is even, which means we're going to have a y-axis symmetry here. With all of that information, let's piece it all together. So first thing, let's begin by plotting our points. We have an x-intercept at negative 1, an x-intercept at positive 1. We have a y-intercept of 0. And now one of the other things we know is our end behavior. We know it has to go up to the left and also up to the right. So it should look something like this. I have to go up to the left. Eventually, we have to come down through and pass through this x-intercept. But remember, we're not going to cross the x-axis. We're going to touch, and then we're going to turn around. Now, when we turn around, we eventually have to make our way up and pass through the y-intercept at 0, 1. From there, we eventually have to turn around to get back down to this x-intercept at 1, 0. Again, we're not going to cross. We're going to touch and turn. And then that agrees with our end behavior here, where we have to then go up and approach positive infinity. I can do a little bit better of a job, because remember, it's supposed to be symmetric. So I'm just kind of go back here and as best I can, try to make it symmetric with respect to that y-axis. The other thing you want to make sure when you're doing this graph, remember it's a polynomial, it needs to be both continuous and smooth, so make sure you're doing nice rounded corners here. Don't have any sharp peaks or rapid turns around, okay? Polynomials cannot turn in a sharp manner. But there you have it. So from just that little bit of information, intercepts, knowing their multiplicity, and the end behavior, as well as a little bit of symmetry, we're able to, by hand, come up with a very nice graph of x to the fourth minus 2x squared plus 1. Let's take a look at the next one. In example 7, we have the graph of f of x equals negative 2 times x minus 1 squared times x plus 1. Let's do it the same way. Let's start off with the end behavior. Now this function is presented in factored form. So to find the leading term, here's what we need to do. We keep this coefficient, so we have a coefficient of negative 2, and then the highest power in each parenthesis is going to contribute to the leading term here. The highest power in the first parenthesis is x, so x to the second will be the biggest contribution from this factor, and then the largest power of x in this parenthesis is x to the first power, which itself is being raised to the first power. So if we multiply this all the way out, you would find ultimately that the leading term is going to be negative 2x cubed. Okay? So that's our leading term, negative 2x cubed. This is the situation where n is 3, which is odd, and a sub n is negative 2, which is less than 0. When that happens, this is the kind of polynomial that's going to go up to the left, and it's going to go down to the right. So when x approaches negative infinity, f of x will approach positive infinity, and when x approaches positive infinity, f of x will approach negative infinity. So we now have the end behavior. Next thing we want to go for is the intercepts. And having it already in factored form is pretty convenient for us. We can just set each of those factors of x equal to 0. The first one will provide x equals to 1. The second one will provide x equals to negative 2. So we have these x-intercepts, negative 2, positive 1. We can discuss their multiplicity. The intercept of negative 2 came from a factor that appeared with a multiplicity of 1, which is odd. And x equals to 1 came from a factor that was raised to the second power, so it has multiplicity 2, which is even. We can now talk about the behavior at that x-intercept. If it's odd, that means it's going to cross through the x-axis. And if it's even, I'm just going to abbreviate it t and t. That means that it's going to touch and turn. So that one's going to touch and turn around. We also can get the y-intercept from this. If we evaluate f of 0, this is going to be negative 2 times 0 minus 1 squared times 0 plus 2, which is going to be equal to negative 2 times 1 times 2, which is negative 4. So we have the y-intercept, which is 0, comma, negative 4. We already have our two x-intercepts, negative 2, 0, and 1, 0. Let's go ahead and plot those. Negative 2, 0 is here. 0, negative 4 is here. 1, comma, 0 is here. Remember, the end behavior for this one should be that it's going to go up to the left, and it's going to go down to the right. You can check this one for symmetry. It's going to be a little bit more involved work, but you would probably have to expand it all the way out and do a test, but this function is going to be neither. Okay, this function will be neither even nor odd, so we don't get any kind of symmetry with it. From here, let's go ahead and fill in our graph. We know that to the left of -2, it's going to have to approach positive infinity, something like this. Now notice that -2, that is a x-intercept that has an odd multiplicity. So it's going to pass through and cross the x-axis as we need it to, because we have to come down here and hit through this y-intercept. Somewhere after that y-intercept, it's going to need to turn around because we need to come up and intercept the x-axis at x equals to +1. Now from there, keep in mind the end behavior to the right is that it needs to approach -infinity. Okay? It's going to go down to the right, and that kind of agrees with what we see here. At x equals to +1, this is an even multiplicity, so it's going to touch and turn around. So at x equals to +1, this graph then touches and turns around, and will be able to approach -infinity. Last thing you might want to do, this looks a little bit odd, the way I have it kind of drawn there. Again, it should be nice and smooth, no sharp corners or peaks. So let me just kind of go back through and pretty it up a little bit. But this would be the graph of the function f of x. Again, found by finding end behavior, the intercepts, their multiplicity, whether they touch and turn at an intercept, as well as some additional considerations, things like intercepts of the y-axis, and also maybe some symmetry.